Okay, in this example, we're going to look at simplifying some radicals. As we simplify some radicals, we're going to be applying a property that allows us to separate radicals wherever there's stuff connected by multiplication inside the radical. So the property that we're using is a root a times b is equal to the root of a times the root of b. It's the property we apply when we simplify radicals. Now, if we look at the first one, we have 32m to the 15th, and we're taking the fifth root of that. So what we want to do is start by checking, just like we have done in the past, is this a perfect fifth power? In the past, we've done square roots, but this is a fifth root, so we want to look at, is 32 a perfect fifth power? And you can see 32 is in the fifth power column. We're just using this chart as reference, so we don't have to go through and make a list every time. If you don't have it memorized, having a chart like that, reference chart, can be very helpful. So 32 is a perfect fifth power. Now with that in mind, we also have to check to see if m to the 15th is a perfect fifth power. If it's not, we have to break things down farther. Well, m to the 15th, if you remember how we dealt with variables in the previous lesson, we would rewrite it as a fractional exponent. So if it was the nth root of a to the m, we would rewrite that as a to the m over n, with the exponent on top and the index on the bottom. So is our exponent basically divisible by our index, or is 15 divisible by 5? Yes, it is. So it is a perfect fifth power. So we're going to go ahead and separate things. We don't have to break things down farther, but we're going to be doing the fifth root of 32 times the fifth root of m to the 15th. The fifth root of 32 is just 2. You can use the reference chart as assistance. For the variables, we can look at it like this. M to the 15 over 5, exponent over index, but 15 over 5 reduces to m to the third. And oftentimes, people will jump in this situation from here to here. Depending on what purpose you're doing this for, you may be required to put in steps in between, depending on the situation. Going for the other one. So same thing here. We want to check, since they're both variables, we're going to check to see if our exponent here is divisible by our index. Well, 20 indeed is, and so is 8. So if we separate it, we have the fourth root of x to the 20 and the fourth root of y to the 8th. Again, we'll change those into fractional exponents, x to the 20 over 4 and y to the 8 over 4, connected by multiplication here. And then we'll just divide. So 20 divided by 4 is x to the 5th, and 8 divided by 4 is y to the 2nd. And that's it for those two. Okay, in this example, we're going to be solving the equation 2x to the 5th equals 64. So we have solved equations like this before whenever it was something like 2x squared equals 64, for instance, when the exponent was 2. And here it will proceed pretty much the same thing. Since x only occurs one time, we're going to be using reverse order of operations. We'll start by getting rid of addition and subtraction. But there is no addition and subtraction in this problem, so that's taken care of. Next, we'll get rid of multiplication and division, so we're going to get rid of the timesing by 2 first. We'll divide both sides by 2, giving us x to the 5th equals 32. So multiplication and division, done. Now we're going to get rid of exponents. And exponents, essentially to get rid of the exponents, what we're processing is we're trying to figure out what to the 5th power is 32. In other words, what is the 5th root of 32. Well, if I use my handy chart, I can figure that out pretty easily. I see 32 in the fifth power column, so the fifth root of 32 is 2. So x will equal 2. Now bear in mind, remember that if the root is even, slash exponent is even, then we need plus minus, because there's two possibilities, the positive version and the negative version. Okay, so in this problem we have a cube-shaped container that has an edge length of 2 centimeters, longer than the edge length of a second cube. The volume of the larger cube is 729 cubic centimeters. When the larger cube empties into the smaller cube, how much water will spill? So if we look at this, here is our larger cube, this picture. And this water is being poured down into the smaller cube. So we first need to figure out how much water, or how long each of these side lengths are, so that we can calculate the volume of the smaller cube. Now it describes the connection between the two cubes as the bigger cube side length being whatever length the short one is, but plus 2. So I know that each of the sides for the bigger cube is x plus 2 in length, while the smaller cube just has x in length for each of the sides. Now the volume of the bigger cube is 729 cubic centimeters. For volume, well, volume is calculated for a cube by the side length cubed. And that's equal to the volume. So if I use this, I know that the bigger cube has a volume of 729 cubic centimeters, and each side length is some number plus 2 centimeters in length. So this gives me a simple formula for the volume of the bigger cube. In a similar fashion, I can write the volume of the smaller cube by doing the same thing. We don't know the volume of the smaller cube, that's what we're trying to find. But we do know that the side length, based on our problem, is x, or the missing side length. These two x values are the same. I should probably use a different color there. Let's go with red. There we go. So those two x's are the same number. So once we figure out one of the x's, we can figure out the other. Now since we're missing two values in this equation on the right, we can't really do anything with it at the moment. However, on the left here for the bigger cube, we're only missing the value for x. Therefore, we can actually solve this equation for x, which will allow us to finish the other one with the smaller cube. So, to get this started, we need to first figure out what to the third power is 729, taking the cube root of both sides. I know I need to do this because there's nothing outside the parentheses besides the exponent. So I will do the cube root of 729. I think that's 9, but I should probably confirm it. Yep, 9. So my calculator told me 9. And my chart doesn't quite go up that far. There's always ones off the chart, but the chart can be helpful sometimes. Anyways, cube rooting both sides gives us 9 equal to x plus 2, which means if I subtract 2 from both sides, I get that x, or the side length for the smaller cube, is going to be 7. Now that I know the side length for the smaller cube, I can go ahead and replace x in the other equation. And then 7 to the third power will tell me that the volume for the smaller cube is going to be 343 cubic centimeters. Now this isn't actually what we're looking for. This question is posing, when the larger one empties into the smaller one, how much of the water will have been spilt? Now, I know the volume of the bigger one is 729 cubic centimeters, but the volume of the smaller one can only contain 343 centimeters. So the difference between the two would be what is spilt. So if we subtract the two, minus 729, there we go. So it should give us 386 cubic centimeters is what is spilt, and I definitely didn't write that 6 right. I just made it a C. There we go. 386 cubic centimeters of water is what is spilt.